You know the feeling. You've spent hours crafting the absolute perfect C++ algorithm. I mean, the logic is flawless. Your time complexity is sitting at an optimal O log n. You hit submit, totally confident of victory, and bam. You're greeted by the ultimate boss fight of competitive programming, time limit exceeded. Well, what on earth just happened? Why did your mathematically perfect algorithm just fail? Okay, let's dive into this. Welcome to this explainer. Today, our mission is to take C++ input-output, which usually feels like this mysterious, slow black box, and transform it into a completely transparent, lightning-fast system. We're going to figure out exactly why your code is lagging, and, way more importantly, how to permanently fix it. So here is our roadmap for today. 1. Meet the C++ streams. 2. Handling input and errors. 3. The stream buffer architecture. 4. Unleashing fast input/output. And 5. Thread safety and beyond. All right, kicking things off with Section 1, Meet the C++ streams. To really optimize our code, we first have to understand the fundamental mechanics of how data actually moves. And it's actually pretty wild, because in C++, there's no special built-in language syntax for streaming data in or out. None. Instead, it's entirely handled by a library of classes, which you primarily access through the IOStream header. So think of a stream like a giant continuous conveyor belt. It's constantly moving items, in this case chunks of raw data, either into your factory, which is your program, or out of it to the user's screen. Now, working on those conveyor belts, we've got 4 main standard stream objects. There's SYN for standard input, Cout for standard output, CR for unbuffered error output, and clog for buffered log output. And here's a really cool detail. Notice how these objects overload the bit shift operators? Those double less than and double greater than signs actually act as visual arrows. They literally point in the exact direction the data is flowing. With SYN, data flows away from the input and points right into your variable. With Cout, it flows away from your variable and points out to the screen. It's brilliant. Moving right along to Section 2, Handling Input and Errors. So how do we actually capture all that flowing data? Well, when we use basic CN extraction, something like CNAge, it's a lot like filling out a form, field by field, which is great, right? But here's the catch. It automatically stops the absolute second it hits a space or a new line. If you try to read a full name this way, you're only going to get the first name. But if you need the whole thing, using the getLine function essentially gives the user a massive blank line to write a complete sentence. If you're grabbing user profile data that has spaces in it, getLine is absolutely what you must use. But wait, what happens when you ask for a number and the user just types the letter A? Well, the stream instantly enters a fail state, and that letter A just sits there, completely blocking the conveyor belt. This is the notorious dirty buffer trap. And if you aren't careful, it will throw your program into an infinite loop. To recover safely, you need a very specific 3-step sequence. Step 1, detect that bad guess at the door, using syn.fail. Step 2, reset the stream's internal error flags with syn.clear. Think of that like telling the bouncer to reset the entry list. And step 3, throw that bad data right into the trash, using syn.ignore. You literally have to do all 3 to clear the blockage. Okay, let's peel back a layer. Section 3, the stream buffer architecture. This is where it gets really interesting. The C++ I/O library is actually cleverly divided into 2 distinct layers. On the high-level side, we have streams, like basic IOStream. Think of this as the tuxedo-wearing waiter at a fancy restaurant. It handles all the formatting, deciding whether a number should be decimal or hex, basically just making it look nice. But beneath that, we have the stream buffers, like basic streambuff. This is the kitchen cook in dirty overalls handling all the raw ingredients. The buffer doesn't care about formatting at all, it just does the low-level, heavy lifting of crunching and moving the raw bytes in and out of memory. Now, because these are generic class templates, they can look pretty intimidating at first glance. But thankfully, C++ gives us handy type defs, basically shortcuts, so we rarely have to touch the raw templates directly. For example, a basic stream working with standard char types is simply called IOS. If it works with wide characters, it's WIOS. And on top of that, the library implements these architectures for specific tasks, which gives us fstream for working with files and stringstream for manipulating strings right in memory. Now for the moment we've been waiting for. Section 4, Unleashing Fast Input/Output. All right, this is exactly how we solve that initial time limit problem and shave literal seconds off our execution times. The absolute first secret, you have to avoid the end-del trap.
When you first learn C++, pretty much everyone teaches you to use endl to end a line. But endl actually does two things. Yes, it adds a new line character, but it also forcefully flushes the output buffer. Imagine flushing a toilet after every single drop of water. That is insanely inefficient. Forcefully flushing the buffer after every single line is an immense performance killer. If you're in a competition, strictly use the new line character, \n instead. Just let the buffer fill up naturally before it flushes.
Okay, and here are the 2 magic lines of code that will fix 90% of your time limit exceeded errors. By placing iosbase.syncWithStudio false and sin.tie null at the very top of your main function, you are effectively cutting the heavy ropes that hold C++ back. That first line disconnects the synchronization between C++ streams and standard C streams. The second line unties sin from Cout, so Cout doesn't automatically flush every single time you ask for input. It's basically like disconnecting a heavy sidecar from a motorcycle so you can finally ride at absolute top speed. And the real-world impact of this is just massive. To put this into perspective, imagine reading a million integers. Standard, unoptimized cin takes a really sluggish 2.0 seconds. But just by adding those 2 untying lines and using \n, we drop all the way down to about 0.3 seconds. That puts us in the exact same fast tier as CCScanf function. And hey, if you're dealing with absolutely massive data sets, like 10 to the 6th power integers and insanely strict limits, writing a custom read function that parses integers byte by byte can get you down to 0.15 seconds. But honestly, for 90% of competition problems, just untying the streams is completely enough to save your run.
Finally, let's look at Section 5, Thread Safety and Beyond.
So what happens when we take our blazing fast streams and throw multi-threading into the mix? Well, the C++ standard library has a few fundamental rules for thread safety. First off, an object is totally safe if multiple threads are just reading from it at the same time. Think of it like multiple people reading the same billboard, completely harmless. But if a thread is writing to an object, you absolutely must protect that data with locks, because multiple people trying to paint over that same billboard at the exact same time, yeah, that's going to result in pure chaos.
But get this. There is actually a fascinating exception specifically for standard I/O stream objects like Cout. The standard actually guarantees that you can write to Cout from multiple threads simultaneously without causing a fatal program crash. Your program will survive, but the output will intermix. It's like 2 people speaking into the same microphone at the exact same time. You'll hear both of them, sure, but your console output is just going to be a jumbled mess of gibberish.
And just to round out our multi-threading rules, it's worth noting how smart pointers like shared PTR handle this. The library ensures that multiple threads can safely read and even modify different shared PTR objects concurrently, even if those pointers happen to share ownership of the exact same underlying resource. It elegantly maintains all that safety behind the scenes. It's sort of like roommates having separate safe copies of the exact same house key. All right, let's tie the whole shebang together. We have journeyed from basic sin extraction all the way up to high-octane, thread-safe competitive programming. Remember your core takeaways here. Ditch endl and always use \n. Untie your streams if you need that raw speed. Understand how your stream buffers can get blocked up by bad data. And, for sure, always mind your thread locks when you're writing concurrently. By mastering your I/O, you've just conquered one of the biggest hidden bottlenecks in all of C++. But, it kind of leaves us with an exciting thought. If standard streams can be completely bypassed and rewired for extreme speed, what else is the C++ standard library hiding from you? Keep coding, keep optimizing, and we'll see you next time on The Explainer.